Alright, what's up guys? In this video we're going to pick up with some vector calculus here, and we're going to evaluate another line integral using Green's theorem. So we're asked to determine the work done by the force field. We're given the force field here, F is equal to x minus xyi plus y squared j, when a particle moves counterclockwise along a rectangle with the given vertices 0, 0, 4, 0, 4, 6, and 0, 6. The reason why we want to use Green's theorem here to evaluate this line integral is because notice here that we were given a rectangle. So if we didn't use Green's theorem, that would mean that we would have to parameterize each side of the rectangle, and nobody wants to do all that. So I'm just going to write down Green's theorem for you, and we'll evaluate this, and I'll post it on the website so you can see the answers. Alright, so this is Green's theorem. There's two forms, circulation form, flux form. But this is Green's theorem. It's the closed line integral f dot dr. We talked about this before. And it's equal to the line integral m dx plus n dy. It's equal to the double integral. R is the region, and it's the partial of n with respect to x minus the partial of m with respect to y dA. So that's going to be Green's theorem. Recall that the partial of n with respect to x minus the partial of m with respect to y, recall that that's just the two-dimensional curl. Okay. Alright, so let's just identify what m is. So m of x comma y, what would that be? Well, that would just be, x minus xy, and n of x comma y, which I'll just write as m and n. It's just y squared. So we just need to compute our partial derivatives. So we need the partial of n with respect to x. Well, that's just 0 because there's no x in there. And then we need the partial of m with respect to y. And the partial of m with respect to y here, it's just negative x. Okay, so we have our double integral over here. It's the partial of n with respect to x minus the partial of m with respect to y dA. So be very careful here because we're going to have two negatives, and this will catch you off guard if you don't pay very close attention to it. So we have 0 minus, now remember this was negative x. Okay, so make sure you pay attention to the sign changes there, and then dA. Okay, so obviously we'll just end up with a positive x. And so we just need to evaluate the double integral at this point. So the limits of integration are just going to be from 0 to 4, from 0 to 6, and we're just going to be left with x. dA here is going to be dy dx. So it's just a double integral now. Alright, so we integrate respect to y first, treating x as a constant, work our way from the innermost integral to the outermost one. So this would be the integral from 0 to 6, and it's going to be x dy. I'm integrating a constant respect to y, so that's going to be xy evaluated from 0 to 6. So this will give me 6x minus 0, which is 6x. Now we move to the second integral now, so it's going to be from 0 to 4, and we're integrating 6x dx. So 6 is a constant, come outside, applying the power rule, that'd be x squared over 2, evaluated from 0 to 4. 4 squared is 16. If I divide 2 by that, I'll get 8. Subbing in 0 just gives me 0. So I'm just left with 8 here. So I have 6 multiplied by 8, which we know is just going to be 48, which is actually your answer. So your final answer for this integral here, this line integral, using Green's theorem, is the double integral from 0 to 4, from 0 to 6. We're asked to integrate x dy dx, and your final answer here is 48. And that's how you get your answer. Alright, so let me know if you got any questions about it. I'll post it to the website. I'll post it on YouTube so you guys can see it. So just let me know if you have any questions. I'll see y'all next time.